thank you all the organizing committee members and for giving me an opportunity to speak on my research topic related to smart grid. And please let me know if I'm not audible properly at any given point of time so that I can increase my voice. Hope I'm audible loud and clear. And today's topic is smart grid future and challenges. And as during the introduction, it has been mentioned that most of my uh, talks related to smart grid are being covered in my NPTEL online lecture. So today I thought of speaking something different, especially taking you to the next level, that is applications of smart grid. Now, when we talk about, and there are two things, as you could see the logos, one from IIT Roorkee and one from MNIT. So currently I'm on Leon from IIT Roorkee and working at MNIT. I'm heading the institution. So my role is at both the institutions. And to beginning, actually, I like to say that I wish to mention that all the participants, we are most welcome to MNIT Jaipur. It's a wonderful campus and looking forward to see all of you in this campus in near future. Now, when you talk about smart grid, the immediate thing that comes to my mind is about renewable technology integration to the conventional grids. To best of my knowledge, our grids are always smart, and just by adding renewable, calling the system smart is not really appropriate. So what we wanted to say is we have seen a lot of deployment happening in the Alba campus itself. So probably we are going one step ahead, using the renewable energy in a very smarter way, and the control techniques especially, which has gone one step ahead compared to previous control algorithms. We'll understand what are the challenges due to the integration and how this can be addressed over a period of time. And to start with, I will talk about a very simple example, which is very timely and also important. This work actually already published in IEEE Transaction and Power System 2016. So I have just captured a bit of essence, or the gist of the whole work actually. And I'm very happy to say the article got accepted in 2016, but we started working on 2012 on this problem. And it took almost 4 years to crack the first smart grid transaction from the lab actually, almost 6 to 8 years back. So what we thought of initially, we all know that the India is the energy security for India is a bit challenging, and we do have shortage of energy in this country. So when you talk about smart grid applications in a developed country and a developing country is altogether different. So my focus today will be dedicated to Indian scenarios, and probably all these technologies can easily be extended to global platforms. Now, what I wanted to highlight here is that whenever you talk about smart grid technology, you may use renewable energy for your vehicle charging, renewable energy for modern power systems. Everything is possible. But in India, the peak energy management become a question. We all know that the peak energy deficit is close to 2 to 3%, almost for last 1 decade. But recently I have been told the peak energy deficit is as low as less than 1%. So what exactly happens? The peak requirement is keep on increasing over a period of time. And why it is keep on increasing? Because the aspiration of middle class Indian citizens are keep on increasing. We all wish to have electric vehicle. We all wish to, for example, have air condition at our home, and not only the bedroom but drawing room and almost complete house. And the cosmopolitan life, the malls, the buildings, the infrastructure that keep on increasing, and it is a good story. But to do so, we need electric energy for each and every element of this progress. Now, when you need to have a lot of energy, you need to generate, okay? And the biggest challenge that the renewable energy that we have added over a period of time, they are not available to you around the day. Means The peak hour, which is probably, let's say, at 6 p.m., neither your solar nor your wind power is available to you. So adding renewable energy, adding energy to the system through renewable energy sources is different. But meeting the peak demand is still unanswered because of its timing. So what we need to do, either we have to go for conventional coal energy sources or nuclear power plant or hydropower plants, which is certainly a challenge for us today. But if you do not have that, the only source of energy is renewable energy. But that renewable energy is available to you at a given point of time when you really do not need it. And hence, the challenge to power engineers begins there. So that's what actually, the things came to my mind and my research stream in 2012. What exactly we can do to address this issue? So renewable energy was very popular, no doubt about it. But how does it help? You see, in Western countries, most likely, they do not have any peak energy deficit at all. So whatever the renewable energy available to them become a top up to their existing energy scenario. But for us, we need energy even to meet my peak energy requirement. And that time I'm not able to add renewable energy at the time when the peak is, during the peak period. And hence there is a challenge for me to address that issue. Having enough energy resources is not going to address the real challenge. So the thought process is there are two way out. The step number one, you have to curtail your peak energy requirements and move them to off-peak hour, which looks very simple in the process of, claiming a demand that, the peak customers can be shifted to off-peak customers. But practically it is impossible because if you are expected to charge your electric vehicle only during off-peak hours, a bit of challenging, okay? Am I right? None of us are really comfortable in charging the vehicle based on the instruction which is coming from the DSO or the distribution management system. We wish to charge as and when required, okay? So that is one thing. Second, perhaps actually your day-to-day devices, if I tell you to switch off your air conditioning during peak hours, which is not really successful because the model doesn't allow you to have a good life. It's a lot of compromise. And hence we need to have a technology where without disturbing the comfort of aspiring, middle class developing nation individuals, we need to have some technology where everyone get energy around the day without any curtailments. So that is where the discussion begins. So there are three things: demand side management solutions for AC distribution system using DC microgrid with storage. So the idea is you have a conventional AC distribution system, which is our old traditional distribution network. Now, if I integrate that AC distribution system into a AC plus DC system, or a DC microgrid with storage system has been integrated with my AC distribution system, then probably the issue related to peak energy deficit can be removed or reduced. So first of all, there are three problems. One, we have a component of solution to peak and off-peak generation. That means during off-peak hours, the storage devices will be charged to cater the peak demand during peak hours so that the flat system load curve is achieved. So the concept in this article of 2016 on IEEE transitional power system was, instead of forcing the customer to move from your choice of engaging your devices into a particular application, why not we charge all my storage technology during off-peak hours and discharge them during peak hours? Means you are not sacrificing your livings or comfort zone. However, the system, enables you to flatten the load curve by charging your storage devices during off-peak hours and discharge during peak hours. So what will happen? My valley structure of load curve, now the off-peak will go little up and the peak will come little down. So the curve may be slightly flatter. Now the second one is the storage technology, because the distribution Demand side management using DC microgrid with battery storage is a promising solution, to best of my knowledge, to feed the loads at peak hours of the present distribution system. Instead of saying customers to move to off-peak hours, start cooking in the midnight through electric uh, or compromise your comfort actually during peak hours, it is better that you use extra energy through energy storage devices and use them during peak hours. Now, the third one is a DC microgrid, which is a new concept at that time anyway. So, introduction of DC microgrid within existing AC distribution system to feed the DC loads will be the viable futuristic options. So, probably there was also an idea that to reduce the distribution losses, so can we not have a mechanism where all my DC loads can be catered through my DC generation itself instead of feeding into AC distribution system? Just here, all of you please concentrate. So what we wanted to highlight, so that was a dream before 10 years, but today it is already in practice. So I'm very happy to highlight that what our research team thought before 10 years, now it is, really being visible in modern, uh, you know, building technologies as on today. So first of all, what we are suggesting that we can have smart meters and DSM controllers connected to each and every devices, and those devices could be anything. It could be electric vehicle. That time we never thought of that electric vehicle can play an important role. So we have not considered, but probably today to loading points actually instead of considering a DC motor and air conditioner, I can also consider electric vehicle here. And then those perhaps actually, can communicate, the devices can communicate to my smart meter and DSM controller through any kind of communication technology. And probably that time it was a Zigbee. And then you need to get certain data, desired consumption curve of a particular day ahead, hourly or maybe 24 hours day ahead plan. And then you can a central processing unit actually will communicate with the utility distribution center, and where if you wish you can also embed bit of actually time of the day tariff structure. So where if you make your energy costlier during peak hours, then probably some of the customers may start using less energy if they are sensitive towards energy price. Okay, and we can also forecast the DC renewable prices, and the overall mechanism can be catered so that all the consumers get engaged, and some of the devices can be curtailed, some of the loads can be shifted, and whole mechanism can be executed. But to do that, there was a bit of challenge. In the previous model, we had no source of actually DC bus concept. So now we are moving to a bit of a larger domain where we are considering there is an AC bus, which is standard AC distribution system. And then we consider one more DC bus, which is a DC microgrid, we so-called DC microgrid. And then we expect actually all the loads of a distribution system, they are DC or AC type. All the DC loads can be engaged with AC load, DC bus, and the AC loads can be connected to AC bus. And however, some of the DC loads can also be connected to AC bus, and some of the AC loads can be connected to DC bus. Now, in the process of doing so, so what we wanted to highlight here that input data from the distribution utility, that means how much AC load I need tomorrow morning at a particular hour, let's say 10 a.m., and the amount of DC load that I need at 10 a.m. can be obtained. And then the time of the day tariff, which is already, available to us in an online platform. So the TOD is known to me, and the DC renewable prices are also known to me. And then the battery maintenance cost and energy cost for battery storages can be defined. So you need to optimize your whole process, that how I really, have to engage my distribution system, because the battery, it is easy to say that charge and discharge, but that will certainly increase my energy cost also. So we need to optimize the whole process. So in that process, finally what we do, at the end, the output of the optimization algorithm gives information to consumers in the form of desired load curve with devising shifting instructions. So what we do, that if you are saying that I need to optimize my electric bill end of the day, then I'll be told that at this particular hour, this much of energy you have to use, and these are the devices need not be used during that particular hour. Now, the question here, when we talk about, you see, this is a practical load curve and of a distribution system. I'm not mentioning the distribution because that time we were working on a distribution system where the data were actually not disclosable, not ND agreement was there. So we are not disclosing those details, but this belongs to an Indian distribution system of Western India, where you could see that, that the blue one is my forecasted load. So we hope that tomorrow, maybe this is the load curve we are going to experience in a distribution system, where actually we are talking about DSM of a AC distribution system. So there is no battery, there is no what do you call it, DC. Microgrid is present there. It is a purely AC system. And once you have this load curve, how I can carry out demand side management activity. All of you, please try to have a look to the red dotted line. This I'm going a bit slow because I know some of the researchers, those who are listening to this talk, can certainly extend their research work if they're relevant to this field. I'll be talking about 5 to 6 research problems today. So I think almost all the research scholars will be benefited if they concentrate a little more. Now, this dotted line is my targeted load curve. The dotted line is my targeted load curve. So what is targeted load curve here? Means when my load is at peak hour, I wish my targeted load has to come down. When the load curve is off peak, the forecasted one, my target will be towards peak. Means I have to pull this blue curve towards red and have to push this blue curve towards the red line. And hence this is my targeted one. Always please remember, the targeted load curve is an inversion of my forecasted load curve. So how do I create this targeted load curve? Because for a given system, load curve is known to me, but the targeted load curve is something different. So ideally what we do, we know the energy cost at each and every hour, and we can take a inversion of that, because the cost of energy during peak hour at this hour, which is very, very high, and if you take an inversion of a high value, that become low, and the price during off peak hour is low, and if you take an inversion, you will get a high value. So that is how the inversion of the price at each and every hour probably will help me to make a curve which is a targeted one and considered to be the inverse of my given load curve. Now, once you have the targeted one and the original one is present to me, and then what we need to do, we have to push some of the loads towards this zone. So the green one, all of you please observe, the green one is my really the final, the load curve in line with the targeted one. But in a practical scenario, all of you please try to understand it is impossible, even next to impossible, to make the load curve flat. Also, it is impossible to meet out your targeted load curve. So it will be not as straight as expected, but it is around that point. Okay, it is around that point. Now, please tell me what we have gained out of it. The peak, what we had, the blue one, the peak of the load curve is now reduced to this point. Okay, so you could see that the load curve, the peak reduction has happened, and hence, for example, in a system you have experienced 2% of peak energy deficit, but through this demand side management, if you reduce the peak by 4%, then instead of 2% peak energy deficit scenario, you are at 2% excess peak demand scenario. Okay, so that is what the DSM activity is all about. Now, if I make this technology a little smarter by taking DC microgrid, so the thought process was, you see, up to what I have discussed till now was nothing new actually in 2012. Many researchers have already worked on that, okay? And now actually the new story begins where we thought that why not the DC microgrid can complement better to AC distribution system. using a battery storage. So we added a storage mechanism during this off-peak hour to push this curve towards up, and also discharge during peak hours, so this load curve can come down. So further you can see the green characteristic, which is still better. So in the first case, we have reduced the peak by 12%. In the second case, the peak has been reduced to 19%. And hence, we wish to claim that in a DSM activity, if you have a DC microgrid in place, probably your DSM activity will be very much successful. And with battery storage technology, it can further enhance to reduce your peak uh, demand requirement, and hence address the peak deficit scenario into the peak excess scenario. These are the detailed theoretical studies. So, what we realized that if you go for a battery technology in place, then the peak reduction can happen significantly better. So here I just like to read it. So this is what a practical load curve. You can see the original one, the targeted one, and finally the expected one. Now, after demand side management, you might have heard that over a period of time, people started talking about demand response activities. So, what is the difference between demand DSM and demand response? Demand response means DR. Okay, so the difference between DSM and DR and the similarities are, a kind of an important topic in 2017-18. So the US Department of Energy defined demand response as a tariff or program established to motivate changes in electric use by end use customers in response to changes in the price of electricity over time, or to give incentive payments designed to induce lower electricity use at time of high market prices, or when the grid reliability is jeopardized. Means you have a system, can you create a responsive mechanism, or I like to add a term here known as price elasticity. Okay, that means there are few customers today. For example, if the petrol price is more, then we go for diesel vehicles. So that means I'm price sensitive towards diesel and petrol price. Okay. Similarly, if the electricity price is more, then I start consuming less. Okay, it is not true always. Few people say it doesn't matter, even it is 500 rupees more, I'm ready to pay, but I will consume even it is 10 times costlier during the peak hours only. Many of you may be aware, if there is a flight you need to ride in the peak hours, the cost is more. Few people don't care, okay, they pay three times of the cost and travel during peak hours. However, some of them wait till 11 p.m. to take the ride, which is not very comfortable, but the cost is lower. So they're price sensitive people, okay, or they are elastic towards price changes. So demand response is something like this, where because of the cost, your behavior actually changes. Now, the main difference between demand side management and demand response, the demand side management is performed only at utility level, at the distribution system level, whereas the demand response is performed at both utility and consumer level. Try to understand. If you see, when you talk about any distribution network, and we are the consumer, so if something happens between both consumer and system level, or system distribution network manager level, so then it is my actually demand response. However, if something happens only at network level without taking care of the customers to a larger extent, then that is known as my demand side management program. So when you talk about the main aims of demand response analysis, so first point is minimization of the total electricity consumption at large. So the main target is the consumption mm, has to be optimized. But all of you please try to understand here, this point may lead to a bit of confusion. Now, if I have a load curve, either you shift those peak load to off peak hour, because consumption is really not going to reduce. Either I have to study 8 to 12 or 2 to 6. Anyway, I have to study for 4 hours or I have to work for 4 hours. So the energy consumption remains same to best of my knowledge. The washing machine has to run whether it is morning or evening, and similarly everything. So that if you plot the area of cross section under your load curve, that area of cross section remains same. Okay, but we like to optimize the minimization of the total electricity consumption. Means because of the price entity and price elasticity, few customers may start become optimistic and they start conservatively use less energy for day-to-day life. Now, the reduction of the total required power generation, certainly, the peak when it reduces, your products also reduces. Promote the idea of green and clean energy, that is fine. And elimination of line overloading. So probably these are the main ideas through which a demand response program is successful, considered to be successful. And ideally, this is how it look like. So probably what we do, we have a ISO, okay, or in India probably you can call it as a CRC, Central Electric Regulatory Commission, and then we have different distribution system operator, DSOs, distribution companies, substations, and then you have it residential, commercial, industrial. But in between, could you see this gentleman who is an aggregator? And aggregator is an important role of balancing out both the consumers and the distribution DSO owner. Perhaps actually this fellow speaks to everyone virtually and see to that, negotiate that this much of energy I will take it from you during off-peak hour with a cheaper price, and then go door by door and connect them through online platforms and advise them to use energy during that hour, which has been made available to you in a cheaper price. Okay. There is no time, otherwise I think sort of time, otherwise I would have given wonderful examples. Before 2 decades we had I mean the telephone tariff, telephone calls, when you make telephone calls, the cost is keep on changing from time to time. So peak hours it is 2 pulses, and then 4 pulses, and then 8 pulses, 1 unit price. So everyone used to speak during evening hours, okay, or late evening, perhaps after 11 p.m. if I'm correct. So similarly, aggregator will help you to buy energy to your industry during a cheaper duration or a off-peak hours. Now the process is slightly interesting here. What it happens, like first of all, the ISO determines the preferred demand volume and time duration that is offered, and then the aggregator receives the load data from the ISO. So means the aggregator receives a command saying that okay, these are the load curves during which the cost will be of so and so nature. And then the aggregator actually select the consumer for their participation into the DR program depending on their availability. Means the ISO says that this is my peak hours, you have to be careful. Then the aggregator instruct the consumers, those are under control and ready to vary their operation from time to time. They will follow the instruction because it's a cheaper option that the aggregator will bring to you. And accounting the number of interested customers agree with the proposed demand response, the aggregator optimize the total demand. Talking to 1,000 customers, taking their data. If I tell you not to give an electricity during so and so hour, or minimize it, or curtail some of the devices, if you are agreeing to that, based on which the offer can come to the ISO back, where the new load demand data is reported to ISO at the local distribution operators. And this is how actually the whole process of demand response works. And keeping that into mind, and then we extended this demand response activity. The first one, the DSM2 smart grid application. And I'm now talking about the second problem where the demand response to smart grid applications. And this work has been published in 2019-20. It's IEEE transition on industrial informatics, where we worked on resilient scheduling portfolio of residential devices, where we brought electric vehicle also into account by minimizing conditional value at risk. And this is, for some extent, to best of my knowledge, it was a very interesting philosophy. What we are saying here, all of you please concentrate again. This is a very 10 to 12 page long article, but I'm just giving you the gist or the essence of the whole article so that you can refer back these articles. Probably you can understand much better after listening to this talk. So you have a main grid, and this main grid, which is through a distribution transformer, and it is available to me through my home appliances. And then the red line, which talks about AC power flows, And the DC, the blue one is my DC power flow. So these are the AC power flows and these are DC power flows. So you could see that because of the electric vehicle, the storage, the PV, uh, electric water heaters, and then DC critical loads, they're all connected through a DC bus. And then certainly you need to have DC-DC converters and so on. So, and there are a few AC devices in our residence which are AC critical loads, and then you have actually washing machines and you know uh, HVAC devices and so and so. But now the question is how those devices need to be optimized. Now, to do so, we need to talk about the energy management device, as you could see, which gathers, all the data. And similarly, you like to also understand the weather data. The weather data is coming to me through an online platform. And then all these data, the data through my residential devices, the data from the weather, and the data through my actually grid operator through smart meter is available as HDAS, that is home data acquisition system. It will collect all the informations and then try to optimize so that the overall, you know, electric consumption and its cost are being actually minimized. So this is the whole philosophy of your uh, resilient scheduling portfolio of residential devices. And today, I don't think so there is bigger challenge, but electric vehicle, just try to understand if you have the option of charging the electric vehicle during evening hours as well as morning hours, okay, peak and off peak both, because it may take 4 to 6 hours for complete charging. So then you will certainly prefer to go for a off peak hours charging, because why do you waste your maybe 500 rupees instead of 50 rupees just because you are not aware when the electricity is costlier and when it is cheaper. But through this technology, probably the vehicle will be automatically charged during an hour where the electricity cost is cheaper. And this is what the resilient scheduling has been carried out. And finally, it is similar to your demand response, flattening the load curve, but it is slightly a better way compared to the previous one. Now, then we'll slowly move to a different advanced technology. And this work, which has been published in 2018, IEEE Transition on Smart Grid. And perhaps actually this was the first article on smart grid from the laboratory. Uh, and there we, because now today it looks a very simple problem, but I still remember in 2015-16, this was a very big problem, and especially we realized in a hardware platform. So this article doesn't talk about simulation; it talks about the real hardware implementation, where the peak energy management using renewable integration DC microgrid has been performed. So what I talked to you in the beginning of my DSM problem, the same problem in 2012's work, which is published in 2015, we again started in 2015 and published in 2018, where the simulation, the thought process, the ideas are being converted into a real-time physical system. So here what we have done, the idea is to minimize the peak energy deficit, okay. And how you can minimize? To minimize, you need to have uh, you have to consume more energy during off peak hours and give energy to the grid during peak hours. And that is how actually the DC microgrid can help. And we are now realizing through hardware setups. So what we've done, first of all, we have a utility grid, which is very simple. And then we have connected PV panels, batteries, and also this ultra super capacitors, ultra capacitors. And then we had actually loads, okay. And we'll perform actually energy management, okay, depending upon the requirements. You see, energy management approach here was, you see, whatever the energy that is available to me through the PV panel will be used for my requirement. All right. And if it is excess, if the load is less than the PV energy or renewable energy available to me, so then they will be charged. All right. And if it is more, then the battery will start discharging. And if it is still more, then I will take the energy from the grid. So the approach is how to minimize energy drawn from the utility grid to my local residential grid. So when I draw less energy, that means probably I have to pay less money to the system. And now the important part here, so you will be only using the grid, and there's another option could be like during the off-peak hours, the utility grid energy can be used for my battery charge if it is not fully charged, so that this can help me to discharge to cater my loads during peak hours. But if it all things are not available, your load is so high that neither through battery, nor from the grid, nor from the PV panel you are able to meet. Few circumstances could be of that nature. That means there is a peak energy deficit. So that case you have to curtail some of the loads based on priority defined in the system. This is a very interesting problem. And so the grid interactive DC microgrid system comprises of PV connected to DC microgrid through unidirectional boost converters. Grid side converter, that is GSC, is connected between the utility and DC microgrid through a transformer for transmitting the power to CG and vice versa. Lead acid battery and alter capacitor considered as storage system. So that time, probably 8, 10 years back, we thought lead acid, which was practically available. But today, some of the researchers, those who are listening to my talk today, can replace this battery lead acid by lithium ions or other chemistries. And if you wish, you can have multiple battery banks also to understand the performances. And you can also probably put your electric vehicle, which was not there in the past. Now, loads are categorized into two types. One is essential load, as I told you, and the other is non-essential loads. So, whenever there is a load curtailment, which is mandatory, so that time probably we can curtail non-essential loads first prior to curtailing the essential loads. So, this is the control scheme which is already being available. And this is the flow chart, the standard flow chart, what I have already explained orally, that how this mechanism, for example, if the SOC is less than 30%, then uh, don't discharge. If SOC is more than 30%, then it can discharge, and so and so. If the SOC is more than 90%, then do not charge. If the SOC is less than 90%, then probably it can discharge, and so and so. Now, after all this mechanism, there's one important challenge here. Like when you talk about distribution system analysis, one problem which was not addressed actually before a decade, that was a load flow algorithm for a basic ACDC distribution network. So what we have done now is we claimed that your system is going to be wonderful when you have both AC and DC system in place, and the DC system can come through a microgrid. But when you talk about the load flow analysis, the potential at a particular bus, either it is a DC bus or a AC bus, we need to know in your control algorithm. Okay. So to understand the voltage at each and every bus, we need to have a load flow analysis. And unfortunately, all our conventional load flow algorithms, those are available in the textbook, they are predominated by AC systems. Okay. So it was high time before 5, 7 years where we thought that, okay, let us also consider about ACDC distribution system load flow algorithm. And probably in late 1880s, three exceptionally brilliant inventors like and Nikola Tesla, and George Westinghouse and Thomas Edison battle over which electricity system is the best one, whether it is AC or DC. And you know the story. I'm not really taking a lot of time here, but due to numerous advantages of AC over DC, AC considered to be emerged as a victorious technology. Owing to the ever increased demand, declining conventional energy sources and technology revolution in deploying renewable energy sources, interest is invoked again towards the DC system that I'm talking today. For example, in the historically AC was predominating, but with the new technology of renewable integrations and smart grid technology, now DC also got into attention of many researchers. So there are various merits of DC system over AC systems, but complete reinforcement of existing distribution system into DC is practically impossible at this stage. We have gone so far. I don't see in 10, 20 years time from now until we are going to replace the AC systems. But certainly we are going to merge AC system into DC system. Probably now, your transportation systems, your uh, especially electric trains and many independent storage data storage centers are purely DC systems today. So researchers are planning a hybrid distribution network system, which is both AC and DC, which is a better choice. But for that, we need to know the voltage solutions. So in 2019, we have came out with a very interesting article, which is also published in ITB Transition on Industrial Informatics, where a network topology-based approach for the load flow solution of AC-DC distribution system with distribution generations have been obtained. So here I like to explain the objective because we know how to solve the load flow, but for distribution system load flow is slightly tricky compared to your AC system. Gauss-Seidel, Newton-Raphson, okay, all those techniques are very popular for AC systems, a loop mesh system. But in case of a DC radial system, we normally prefer a backward forward flow algorithm. Okay, those who are not referring, please refer to Krusting, uh, and where in the chapter 10 you can easily understand how this load flow algorithm is very nicely described. Whereas if it is a AC DC system, so probably the challenge begins. So to develop an efficient load flow strategy for AC/DC distribution system consisting of distributed generation and various types of power electronics converters. So here what happens, let me say, if my, the system which is the orange line, which is my AC grid, and the blue line, which is my DC grid. So this is my utility substation. And then you get your AC buses, and those AC buses are converted into DC buses. And now it may so happen that DC bus convert again to AC, and some of the points where AC bus is converted into DC. So you have a AC DC system where the power is flowing through AC, converted to DC, then DC to AC, AC to DC. All combinations are possible. And for that system, I need to know the voltages at each and every bus, which is not so easy. Now, the different methodology takes the advantage of the topological aspects in this proposed approach. We have used a bit of graph theory concept, where it takes the advantage of the topological aspects of AC/DC distribution network and solve the load flow problem directly, utilizing the notions of graph theory and matrix algebra. The proposed algorithm embeds the mathematical model of distributed generators and various operating modes of power converters. So these converters and the renewable energy sources are important components that need to be modeled. So you could see in the AC bus, you have AC diesel generators, distributed generators, AC loads, DC loads with conversion, and DC distributed generations with converters. And similarly, it happens for DC bus. So we have taken many, different networks we have designed actually, where you could see again there is an AC grid, and then finally there is a DC grid. The difference between previous one and this one is it's a very simple network, but always we try to create a loop. Okay, so it is not necessarily applicable to only radial networks in a distribution system, but even for a larger mesh. Because when you have AC/DC network, most likely you will end up with actually a couple of meshes. So that is what it will be thought of. So the main thing is there is no LU decomposition, matrix inversion, and backward forward substitutions of these admittance or Jacobian matrix ensure fast convergence of the proposed technique. Utilization of linear algebra makes the load flow solution computationally very, very efficient. The proposed load flow technique proves its robustness and efficacy for large radial and mesh distribution networks having wide range of R by X ratio. So we have validated that this model is actually really working well for almost all the methods. So either it is a distribution system with different R by X ratio, still the system is going to work very nicely. Coming back to the setup, that actually we developed at IIT Roorkee. This is, perhaps I'm proud to say, it is my lab, and this is what we've developed. And the very interesting thing is that we had a real-time digital simulator provided by the institution, and you could see there is a power amplifier. So this is probably close to 10 kVA power amplifier. And the left side you can see there is a 15 kVA power amplifier that they have been imported from Germany through project grants. And this is my DC microgrid bench. Okay, and this is the AC microgrid bench, and something is not visible where you have all emulators, wind turbines behind the PCs. So probably this is my DC bench, this is my AC bench, and we used to simulate the whole AC-DC microgrid together. And they have been integrated. Outside there is a connection. Rooftop we have PV, over the through this cable actually you get all the energy which has been produced in the rooftop, and they've been connected to the main grid also. So very successfully, we call it as an admired lab at IIT Roorkee, where the smart grid hardware test bench, which has been developed through support of 6 different international projects, where this ACDC microgrid is operational today and could able to exchange energy with, and independently it can operate as well as it can be integrated easily to the main grid. And this is what very interesting, my final conclusive slide, where what I wanted to highlight here. Now let's say, though this problem is still unanswered, but this is what actually people can try if you wish so. You see, we do have actually DC microgrids, okay? Each and every building do have a DC microgrid. Each and every city will have hundred of microgrids. But the nation will have actually millions and millions of microgrids today. For example, the Alba campus itself do have a microgrid. IIT Roorkee will have another microgrid. IIT Delhi will have another microgrid. So there are thousands and millions of microgrid one day this country will experience. Now, when you talk about a distribution system peak reduction, which is very easy through a local system, okay, small system. But the challenge here, being a developing nation, can't we not integrate all the microgrid and operate them in such a manner they all complement for my peak energy deficit challenges of this nation? And hence, the national characteristic of the load curve will experience a peak reduction if all the microgrids across the country, okay, actively contribute to the peak reduction in whatever best way it is possible. It's a very, very interesting problem. I mean, to me, it is unanswered, but certainly one day we will be able to answer this question. And so, what we have tried to do is that this is the India map. Okay, so we have captured a a large substation, 400 kV substation, and which is in the Rishikesh, and then from there we slowly we reach down to IIT Roorkee lab, where this is the physical system to be. Okay, and everything, the whole national grid can be simulated uh, to a particular level of voltage, let's say 132 kV or 33 kV, depending upon your size of simulator you have. And you can keep one physical system and rest could be non-physical. And assuming that everything is, if integrated and successfully operated, what percentage of peak energy that can be reduced in the network? And this is a question in front of you to be answered in future. And what do we want to say? Mainly addressing power imbalance and security of low carbon integrated distribution and transmission network. A nation as a whole, ancillary services to support utility during various faults, we can help each other. Reduction in large energy deficit using demand side responses, and advanced load flow studies with network pricing can be explored. So with this note, I am coming to an end. Thank you very much for your kind attention.
So thank you very much, sir. Please accept this e-moment from our side.
Thank you. Thank you very much. Namaskar.
Thank you very much, sir. Thank you very much for being with us.